Hello and welcome again to my Physics Online video lecture series. In today's video, I'm going to be talking about the concept of torque in physics. Before I get too far into this video, I'd like to note that torque is, in some sense, from a physics perspective, it's defined as sort of like a twisting kind of force. So it's a force that makes things want to twist or turn about an axis. It's not necessarily to be confused, however, with the centripetal force. Recall that an object that's moving in a uniform circular motion has to have some sort of force that points towards the center of the circle at all times. So if it's moving around like this, then the force is always pointing towards the center of the circle, and that's causing it to turn. If I have something, though, that I'm trying to twist, then I'm going to apply a torque to that something. And so that torque is like this. It makes the object not just move about on a circle, but sort of like speed up or slow down in its revolution. So we will ultimately see, albeit not in today's video, that torque is related to angular acceleration and actually ultimately to another concept called angular momentum. Those are for future videos, however. So there's not going to be much of a recall review part to this video because it's the first of another sort of series, which is rotational dynamics. What we just want to do is define for ourselves torque and how it's determined. So torque, we usually use the Greek letter tau. It is a vector, and the way that we define torque is that it is the cross product R cross F. So this right here is what's called a cross product. So cross product. I don't believe that I have introduced cross products other than maybe in the math review in my introductory physics sequences, if you're watching all the videos in order, of course. And so it might be worth noting what a cross product is, which I'll do momentarily. Before I do that, though, it's worth having a little diagram to kind of explain what's going on. So, simple case, imagine that I have like a square-shaped nut head like this, and I've got a little wrench that I'm using to try to loosen the head of this bolt. Okay, so it's a square shape because I can't draw, but it's a bolt. I've got a little wrench that I've sort of attached to it. Here's a little crescent wrench piece that you use to loosen or tighten or whatever. And to attempt to loosen this bolt, we pull upward with some amount of force like this. So we'll call this the force vector that's being applied. Maybe it's being applied at this location on the wrench. This right here is sort of the center of the bolt. And so this vector that goes from the center point over to the location where the force is being applied, this is my R vector for that cross product. So this defines those two things. Note that if I grab the end of the wrench like this, that the R vector is much longer than if I grab near the head. And if I get rid of the wrench entirely and just try to loosen with my fingers, I have a much lower R vector still. The R vector will be very small. So what that means is that, well, we basically just need to know how do you take this cross product R and F. And the answer is that the magnitude of the torque, which I'm going to label as tau without any vector signs on it, is equal to the length of the vector R, so the distance basically, times the force being applied, times the sine of the angle between R and F. So that angle is basically right, in some sense right here. And more properly, if I were to move the F vector over, so if I take this pair of vectors and treat them as if they both start and end in the same location so that they're like this, then this angle theta is actually the angle running counterclockwise from R to F. So here's theta, here's F, here's R. Okay, so note that among other things, if I reverse the order of the cross product and do F cross R, that if I continue counterclockwise, instead of having basically a 90-degree angle here, I'll have a 270-degree angle here. If you take the sine of 90, you get +1. If you take the sine of 270, you get -1. So if you reverse the order of the two vectors in your cross product, you also reverse the direction of the resulting vector. Now, what direction is this vector pointing in, this torque vector? So I've given us the magnitude. The direction actually points perpendicular to both R and F. So we could write that in terms of tau as a vector and just say it's perpendicular to R, and tau as a vector is perpendicular to F. Now, if R and F happen to be collinear, then this angle theta is either 0 or 180, and that makes the sine of the angle 0. And so the torque will be 0, and we don't have to worry much about direction at that point. If they're not collinear, then R and F are in a plane together somewhere, and tau will be perpendicular to that plane. We usually denote this using either a circle with a dot in it like this to represent that it's coming out of the screen towards you, or a circle with an X in it to represent into the screen away from you. Now, the right-hand rule essentially dictates whether these are in or out. So this right here would basically represent a positive vector. This would represent a negative vector. So if I have a sine of theta that is positive, and I've drawn the two in the plane of the screen, then my vector will point out of the screen. If I have a sine of theta that's negative, then the vector is going to point into the screen away from you. Put differently, you can use what's called the right-hand rule. And the way that that works is that your fingers of your right hand start off pointing in the direction of the first vector. So maybe they point in the direction of R, and then they curl until they point in the direction of F, and then if you stick your thumb straight out, it will point in the direction of the resulting vector. Unfortunately, because of the way that my recording system works here, I can't really demo that very well because stuff gets mirrored on screen versus what I'm doing. And so it's not going to be very helpful for me to demonstrate that in this particular video. But essentially, what I've done here is I've started off by just placing my hand here. So my hand is like here, and my fingers are pointing off this way. And then I'm curling them so that my hand is basically like closed or partially closed like this. And I'm making sure that in doing that, I've moved my fingers from pointing from R to pointing to F. So here's like closed fingers. And in order for my hand to be doing that, my thumb has to be pointing out of the screen at you. So that's basically the best I can do for a right-hand rule demonstration with the setup that I have. But you can remember, if you'd like, that we always go counterclockwise from R to F. We take the sine of the angle, and if the sine of the angle is positive and you've drawn your vectors correctly, then the resultant will be pointing out of the screen. And if the sine of the angle ends up negative, it points into the screen. So that's how you can get it without having to invoke the right-handed rule. The way that this cross product is determined is rather complicated if you don't have unit vectors. And in the algebra-based course, we wouldn't necessarily have unit vectors. But if you know how unit vectors work and you want to take a cross product, basically what you end up doing is saying, let's let R represent, let's say, x I hat plus y j hat plus z k hat, and let's let f represent fx I hat plus fy j hat plus fz k hat. So if I want to do the cross product R cross F, what I actually do is take the determinant of a matrix. So that's some big words for you there. If you don't know matrices either, this isn't going to make a lot of help, but the end result will work out for you, so you can just write it down if you want. Basically what I do is I write my unit vectors along the top row. Then I write my x, my y, and my z, my position terms. And then I write my force terms, fx, fy, and fz. And the determinant of this matrix is going to be y fz minus z fy times I hat plus z times fx minus x times fz times j hat plus, and then for k hat I have x fy minus y fx. That's in the k hat direction. Now, in an algebra-based course, we don't really do the full cross product like this very often. Instead, you usually just want to use these results right here. It's worth noting, though, if you know your cross products, or if you know your unit vectors, I hat cross j hat gives you k hat, j hat cross k hat gives you I hat, and k hat cross I hat gives you j hat. So this is your relationships between your x, your y, and your z directions for what it's worth. This will also guarantee that if the two are in the same plane, you'll always end up with a cross product that's perpendicular to them. Let's do a quick example to wrap up, and it will be just of the regular polar form, let's say, of finding the magnitude. So let's say you want to loosen a tight bolt, so you apply a force of 80 newtons to the end of a wrench 30 centimeters long from pivot point to force application location 85 degrees from the wrench's handle axis. How much torque is this? It might help to draw a little diagram. You have your bolt here, your wrench is here, so this right here would represent R. You've applied F in this direction right here, F, and this right here represents your 85 degrees. So tau is R cross F. It asks how much torque, so that's just simply tau, the magnitude. So tau is RF sine theta. Theta is actually going to be 85 degrees in this case. So what we have is tau is equal to 30 centimeters, which is 0.30 meters, times a force of 80 newtons, times the sine of 85 degrees. Make sure your calculator's in degree mode. This ends up giving you 23.90. So if we round it to 3 sig figs, just to contrast it with saying 24, it'd be 23.9, but at 2 sig figs, we'd say 24 Newton meters. There's only 2 sig figs in this problem, so we should probably round it to that. All right, that's all that I wanted to cover in today's video. Maybe I should make one other little note, which is that this pivot point that has been labeled over here is also known as an axis of rotation, and so you can only really define a torque relative to an axis of rotation. So let's make a little note of that before we close. So again, this is the axis of rotation, and it, just like the torque, this sticks out of the board or out of the screen and into the screen. So that's now all that I have for today's video. Hope you learned something from it, and as always, thanks for watching.